Okay, thanks. Thanks to the organizers for inviting me. Let me just start by saying that I too feel very lucky to work in a field that Menachem works in too, and to be able to count him as a friend. We haven't actually collaborated on anything, but we did have one close encounter, a few actually, but one in particular that has to do with the other MM, MM32, which led to a sea change for intermodal theory. I mean, what I'm talking about today, it's hard to imagine without the work of Menachem Magidor and Shelah in '84, I think it was. So it's a nice example of something that Menachem was talking about, and he's talked about on other occasions. In this field, we're all from different angles uncovering one truth, and you can just never discount the possibility that something discovered here is going to get used over there. So, all right, so I'm going to talk about a new result on, it's about 8 months old, on the existence of canonical intermodals with large cardinals. Theorem is under a big hypothesis, iterability hypothesis. So suppose V is uniquely iterable for normal iteration trees, nice normal iteration trees. That means every such tree has a unique cofinal well-founded branch. It's a major assumption. Okay, suppose also following large cardinals, there's a superstrong, and this is probably all we need, but let me add arbitrarily large woodens. Okay, then there is a canonical intermodal M such that M satisfies GCH, which are sort of code words for has affine structure. It satisfies the large cardinal hypothesis. There's a superstrong. And it knows how to iterate itself. So it satisfies I am iterable. Okay. Okay, so some remarks on that. First, if you drop the I am iterable part, it's ordinary extender models work. Okay, and that's goes back to work by Mitchell and me, which sort of completed that phase of the reorientation of intermodal theory. Actually, you need something that Itai and I did a little bit later. Okay, so it's been known for a while, dropping I am iterable.
Do you preserve the protocol solutions stuff?
Yeah. Yeah. Okay. On the other hand, L of E won't work for 3. That is, no L of E model that has a wooden cardinal thinks that it's iterable, does it? Even though it ought to be iterable if we're, if we've got a good construction for it, but it will be iterable. It won't know its own iteration strategy. Okay, so it doesn't know why it is what it is in some way. So you must add the strategy. The idea that adding the iteration strategy to the model is something you should do, and that it's more canonical information is due to Hugh. And it came up in the context of analyzing the odds of determinacy models. So for n model of 80 plus that's not too large, so L of R is not too large, but you can go up to the minimal model of 80R plus theta regular and a little bit beyond that. So in determinacy models that are not too large, M equals HOD up to theta in the sense of the model N works for 1, 3. That is, fine structure knows how to iterate itself. And, well, but they're not too large, so you don't get up to super strongs. You can get up to many wooden cardinals, basically. Okay, so we can analyze the HODs in, now, these are fine structural models, but they are a little weird in some way. Or, the hierarchy for M is extender biased. So one has to be very careful about adding the iteration strategy to this model. Add it very slowly in a way that's sort of determined by the model N that you're working in, actually, the AD plus model that you're working in, because we don't have a general comparison, or did not have a general comparison method for the more natural construction. Okay, yeah, so I should credit, wooden Sarxian. Okay. I believe that the model in this theorem can be taken to be of the form HOD N for N up a model of 80 plus. That is, I think I see how it goes, but it's not on paper. This one is on paper now. Okay. But one remark, this is not analyzing HODs of 80 plus models up to super strongs under the theory 80 plus. You prove that this determinacy model exists, which has the HOD with a super strong, by starting in V with a super strong and this iterability hypothesis. Okay, so it's not an optimal thing as far as analyzing the HODs of determinacy models at all. Just makes a point that under this hypothesis, they can have very large cardinals. Okay, I'm just going to try to outline a few of the major ingredients of the proof. Okay, so first we'll say something about the first order form of this model M. So I'm calling these objects least branch premice. This is a method of adding the strategy that Hugh had looked at earlier. It's not this, this extender biased one where you add it slowly. Instead, you just, whenever you see an iteration tree, whenever the model sees an iteration tree that's played according to the amount of the strategy that's been added so far, it tries to add the branch that that strategy picks. It looks at the least, it should be least tree missing a branch. Add the appropriate branch. So no particular care is needed. Okay, these premice have iteration strategies. And if you pair one of them with its strategy, you get something called a least branch Hod pair. Hod pair because they're used to compute the Hods of determinacy models. You need a method of constructing such objects, and basically you when you add extenders to the model that you're building, you make sure that there's an extender in V that restricts to that extender, and then iterability comes from the hypothesis that V is iterable. Okay, and then you need a comparison lemma. For these least branch Hod pairs. Okay. Technically, this is all, how's that? Least branch Hod pairs. That's a pair of a least branch premouse and its strategy. They have to be connected in a certain way. Technically, this is really the work that Bill and I did, volume 2. That is, although this intermediate development of the theory of Hod is the reason it exists, technically, none of that makes an appearance. Okay, so it's been kind of fun to go back and relive writing that paper. Okay, so let me just sketch some of these ingredients. So first, what's a least branch premouse? It looks like it's a structure that has a universe, has epsilon. It has an extender sequence, and there's a symbol, the E dot, for that extender sequence. This consists of the extenders added before you got to M. So the information accumulates as you go along. These are the extenders you added before you got to M. Then we have a predicate for the new extender. But of course, you don't add new extenders at every stage, and there's some rules. When you're not adding a new extender, you have a placeholder, empty set. Okay, then we, yes? Yeah, this is their what are called acceptable J structures. So amenable structures with a local form of GCH. There's a paper, Schindler and Zeeman in the handbook on sort of basic fine structure theory for these objects all of those definitions work, so you can just take it over, project and parameter and everything. There's nothing new there. Okay. Okay, so then you have the strategy information added so far. And then you have a predicate for the new branch. If the missing branch for the least tree missing one, or if you're not adding one at that stage, empty set. Okay, so that's the first order form.
What is the tree for which you find in your branch?
I'll say that a few more phrases. I'm not going to say too much, but let's see. So what are the rules? You need to, it's a structure satisfying certain axioms. And the axioms or rules for extenders, they're just Jensen. I'm using Jensen indexing. So you should have a coherent sequence. That's the main thing. And then Jensen index. That is, if we let lambda f be the image of the critical point of f, for that value of lambda f, E is indexed, f is indexed at lambda f plus of the ultra power of m by f. Okay, so there are other indexing schemes possible, but this is a good one. For the strategy, okay, all I planned to say was use b dot of m to add a branch for the m least tree T that's by the strategy that you've accumulated so far, such that the strategy that you've accumulated so far hasn't told you a branch. Okay, so and then there's got to be some rules about when exactly you do that, but they aren't too enlightening. So and how you do it as an amenable predicate, which takes that's an idea of Hugh that if you let the length of tree there's a way of doing it as an amenable predicate that I don't want to talk about. Okay. Okay, so that's all the ideas. You can formulate these as a set of axioms about your structure, and they're very elementary. There's something called Q sentences, which means they're preserved by sigma 0 ultra powers and sigma 1 Skolem hulls, which is something that you want. Okay, so an ultra power of a least branch premouse is a least branch premouse. Okay, some notation. M restricted to the pair nu k is the nth level of M considered as a k sound premouse. Yeah, so I should have added amongst the first order requirements, M should be K of M sound. So every pre-mouse has attached to it a natural number, which is the degree of it represents some level of the Levy hierarchy, and you're demanding that the structure be sound at that level, that is the Holovitz projectum and standard parameter. Okay, so imagine that as part of the information in M. Okay, so M restricted to nu K is go down to the nth level and consider it as a K-sound pre-mouse. Okay, pi from M into N is elementary if and only if, well, roughly it's sigma K plus 1 elementary, where K is the nth of the two degrees of soundness, K of M and K of N. Okay, so M and N tell you what degree of elementarity you should demand of the embeddings between them. Okay. What's that? Center's better. Well, I did something to get it offline, I think. Okay. And finally, we say that P is an initial segment of M if and only if it's M cut off at one of its levels considered as a K-sound pre-mouse. Okay. So the levels of information are tracking all the levels of the Levy hierarchy as you go up. Okay, so that's what a least branch pre-mouse is. If I were to try to define what a pre-mouse is in this extender biased hierarchy, it would take another hour. So this is much simpler. Okay, a least branch Hodge pair. It's M together with a strategy. The strategy acts on stacks of iteration trees. We'll say S is an M stack if and only if it's a sequence nu I, ki, ti, I less than or equal to n, such that T0 is a normal iteration tree on the original model M cut at nu 0, K0. And in general, Ti plus 1 is a normal iteration tree on the last model of Ti, that's called M infinity of Ti, cut at nu I plus 1, ki plus 1. Okay, so the M stack looks like you take a tree on M, you go to the last model of it. Okay, now you can chop down that model. Actually, we could chop the first one down too. And then build a tree on that, go to that model, chop down, and et cetera. Okay? These trees are normal. Normal we can take here to mean first the lengths of the extenders, which are the lambdas. Lambda of E alpha should be less than lambda d beta t for alpha less or equal to beta. That's what is. And we don't overlap along branches. So if alpha plus 1 is t below beta plus 1, then the lambda of E alpha is less than or equal to the critical point of E beta. Okay, so this is actually weaker than the usual normality condition, but it's good enough. Okay. A complete strategy for M is a omega strategy that acts on all M stacks S that are by the strategy. And what's it do? It gives you, for the last tree in the stack, it gives you a branch. How's that? Yeah. One could go to infinite stacks, but it's more technical, and we don't need to. Okay. Okay, so that's the complete strategy. The point is, it tells you how to iterate every last level of the model for every kind of iteration tree you could think of at, a completely fine structural level. So it's all the strategy information. We'll keep the theory. Given any iteration strategy, omega, so if we have a stack that's by the strategy, then we can look at a derived strategy which acts on extensions of that stack, namely omega s of t is omega of s followed by t. Okay, so that's the tail strategy of omega. And now we can say what the least branch hot pair is. M should be a least branch pre-mouse. Omega should be a complete strategy for M. For S in some V delta, which is the domain of the strategy. So we don't demand that they be a proper class. Okay, so there's some domain of the strategy. Omega has the following good properties. Omega is self-consistent. I'm not going to explain these I'm not going to write out formal definitions for these, but let me just explain them. Self-consistent says, well, okay, I could have two different stacks that get me to the same model. How I iterate from then on shouldn't depend on how I got there. That's actually called positional. That's a strengthening of self-consistent that is also true of the strategies. But you can think of it that way. I didn't want to build it into the formal definition. There's some weakening of that that's the formal definition.
Basically says that what you do in the strategy doesn't depend on the previous levels of the stack.
Right, it's just where you arrived. In particular, you know, I could chop M down once and then chop it again. The strategy I get to at the bottom should be the same as just taking one step of chopping it down. Okay. So self-consistent has a property called normalize as well, which I'll explain in a second. Strong Hall condensation. Okay, strong Hall condensation says, suppose I take a Skolem-Hall, well, weak Hall condensation says, suppose I take a Skolem-Hall of the universe where M's in the transitive part. Then if I have a tree T that's by omega, it collapses to a tree that's by omega. So any hull of a tree by omega is also by omega, as long as I leave the base model fixed. Okay, strong Hall condensation strengthens that. And you know, says just what elementarity you need to make this work. Okay, so that's pretty natural. And normalize as well, I'll explain in a second. The final thing is the internal strategy of M should be consistent with this omega. So the strategy information that's been fed into M should be omega. And that should remain true as we iterate. In other words, for S, a stack by omega, last model N, if you look at the strategy predicate of N, it's contained in the tail strategy. So it's consistent with the tail strategy. Okay, so that's it for the objects that we want to construct. I haven't said what normalizing well means, and let me just, this time's really short. Draw a picture. Okay. Suppose we are given, I'll just draw one instance of it. Suppose we're given M goes to some N, goes to some P, where T and U are normal. So we have a stack of length 2 where we don't actually drop on, just for simplicity. We don't do any of that cutting off part. Okay, so we have a stack of 2 normal trees. Then there is a natural, let me just say, a minimal normal tree W of T and U, such that we have the following. Okay. Okay, so we can capture the action of this stack by one single normal tree in a sort of minimal way. Okay, one has to define this, but it's sort of a lot of just rearranging ultrapowers. Okay, shuffle. Okay, so normalize as well means one instance of it is if that that the stack TU is by omega, if and only if this normalization is by omega. Okay. And then, well, we want this actually for any finite stack, and that's the full normalize as well. So it respects the normalization process. Okay. Maybe I should leave that too late. Okay. One really elementary thing you would want, if n omega is a least branch Hod pair, then every elementary submodel of it is too. Pi from m into n is elementary, then m, and the collapse of the strategy, which is something, the pullback of the strategy, which is called omega pi, is a least branch Hod pair. So omega pi is the pullback strategy. Omega pi of t is omega of the result of lifting t. If we have a tree t on m, we can use our map pi to copy it over to a tree t pi t on n. Use the strategy here and you let that guide us down here. That's called a pullback strategy. Okay, and you can show that these properties, they're preserved by pullbacks. It's a bunch of diagram chasing, which is pretty much what all of these arguments are. You just chase the right diagrams and things fit together. Okay. Okay, so that's what a least branch Hod pair is. I've got just a few minutes to say what a least branch background construction is. So it's a sequence of these least branch Hod pairs. They're indexed by pairs nu k, kth level, or the nth level considered as being k sound. We include background extenders for the extenders that are added. So these are the F star nus. Okay. Each of these guys is such a thing. F star nu is a background extender for the nth extender. The last extender of M nu 0 if this exists. That is, if this is not empty. So it's a nice extender over V. And then what's omega nu k? Well, S is by omega, if and only if. Oh, I should have said, let's fix our strategy for V, which we exist by hypothesis. That's the strategy that we're feeding into our model. Okay. Well, but there's some slippage between the model here and the background universe. So you take an ultrapower on the model here, that's not the same as taking an ultrapower on the background universe. There's some embedding going on, and you have to keep track of those. So there's a lifting process. So the lift of our stack, which was on M nu k, and the lift under the construction. The construction is telling what background extenders to use when we lift. This should be by sigma star. Okay? So we put the sigma star information into the model that we're building, and that's the construction. Okay, I'm out of time to say anything more about the construction and the comparison lemma. I'm also out of time for, but let me just say, let me just finish by writing down something. So I want a comparison lemma for least branch Hod pairs. Let P psi be such a thing. With P countable. Suppose psi is universally bare. Okay, so there's the remnant of the descriptive set theory that this, our strategy should be universally bare. Let C be some construction. This is just an abstractly given Hod pair. Let C be a construction. And let me assume, it's not really necessary, but let's assume that the length of C is a wooden cardinal. Okay, so I have this very long construction, lasted all the way to a wooden cardinal. Okay, then there is a pair nu k such that, and a normal tree T on P that's by its strategy such that you've iterated yourself into M nu k and omega nu k. This is let's say the last model here is Q. This is Q and psi sub T. Okay, so basically every one of these abstractly given Hod pairs iterates into some level of the construction, of this bigger construction. That means you can compare two of them by just looking at which level of the construction they iterate into. That's the comparison then. Okay. And then from that and building on that, you can sort of carry out the work, the fine structure and iteration trees work, and to get the theorem that we started with. The key to this theorem is the normalizing well. Well, and actually all the properties of the least branch Hod pairs come into why this theorem works.
What is Q?
How's that?
What is Q in Prism?
Q is the last model of this tree. So we're having P iterate to some Q.
And you have any assumption about
How's that?
non-dropping?
Yeah, it's a non-dropping tree. So in other words, some level of the construction is an actual iterative P. Okay, thanks.